In this video, we're going to talk about elliptical change of variables. So let's jump right into our fact and we'll try to understand what we're doing here. Let's say we want to describe or parameterize the region inside the ellipse, x squared over a squared plus y squared over b squared equal 1. So a change of variables that we can use to describe this region is to say x equals ar cos theta and y equal br sine theta, where a and b squared are what we see in the denominators here. And the r and theta values here will range between 0 and 1 for the radius values and 0 and 2 pi for our angle. So let's see if we can draw a picture of this geometrically and try to understand this parametrization. So we've got this ellipse, x-intercepts would be plus or minus a. So let's say a is there. Y-intercepts plus or minus b, let's say b is there. And so we're getting this ellipse that looks something like that in the xy plane. And we want to come up with a way of describing all the points inside this ellipse. So the idea is that if we use x equal ar cos theta and y equal br sine theta, and we let theta range from 0 to 2 pi, then certainly we'll be traveling all the way around this ellipse. And by letting the r values range from 0 to 1, you can see that these coefficients are going to range between 0 and a for the x value and 0 and b for the y value. And that's just going to be the perfect coefficient to allow us to go out this far in the x direction, that far in the y direction, and to then capture all these points within our ellipse as we travel around from angle 0 to 2 pi. So that's the change of variables we're going to keep in mind as we jump into our next problem. So we want to evaluate the double integral over r of e to the 4x squared plus y squared dx dy using a change of variables. And the region r is the region inside this ellipse. So we're going to go through the same 4-step procedure as we did in our previous video to change variables for this integral. So first thing we're going to do is rewrite the region R. And based on the discussion we just had a minute ago, we know there's a specific way to parameterize the region inside an ellipse. Okay, so let's look at the denominator squared here for our ellipse. So what's playing the role of a squared here is 1. So if we just use the positive values of a and b, then we could say a equals 1 and b squared here is 4, so b is going to be 2. All right, so let's just go back to our discussion above and add just a little bit more detail here. We're using the positive values of a and b when we set up this parameterization. So I write that just to be totally rigorous and clear about how we're choosing a and b. All right, so choosing a equal 1 and b equal 2, we can write down our new variables then. In general, x is going to be ar cos theta. So in this case, x will be r cos theta. And in general, y is going to be br sine theta. So in this case, y will be 2r sine theta. We need to record our range of r and theta values as well. So our radius is going to range between 0 and 1. Theta will range between 0 and 2 pi. And that'll be important when we set up our double integral. Okay, next step, we are going to rewrite our integrand using our new variables. So let's look up at our integrand here. It's an exponential, and in the exponent we have 4x squared plus y squared. So maybe let's just deal with that 4x squared plus y squared first, get that rewritten, and then we'll write the entire integrand. So let's take 4x squared plus y squared and let's sub in our new variables. We've said that x is r cos theta, so we've got 4 times the square of r cos theta, plus we've got the square of 2r sine theta. So let's see if we can simplify that. That's going to be 4r squared cos squared theta plus 4r squared sine squared theta. And we can factor out the 4r squared to get cos squared theta plus sine squared theta. And that part there is just going to give us 1. So in other words, that 4x squared plus y squared becomes 4r squared. So we can say our integrand is e to the 4r squared. And that's now completely expressed in terms of our new variables, r and theta. Okay, so now that we've rewritten our region and our integrand, we're going to actually calculate our correction factor. So what we want is to find the absolute value of the Jacobian as we move from our old variables to our new variables. So I won't worry about the absolute value just yet. Let's think about our Jacobian. And so by definition, that's going to be a 2 by 2 determinant. Start with your first variable x, take partials with respect to your new variables, and then in the second row, deal with your second variable y, take partials with respect to your new variables. Okay, so I'll do a little bit of writing on the side just to remind us what x and y are so that we don't need to keep scrolling back. So we said x was going to be r cos theta, and we said y was going to be 2r sine theta. So we've got that in front of us, and let's calculate our determinant. So x sub r is going to be cos theta, x sub theta minus r sine theta, and then for the partials with respect to y, 2 sine theta and 2r cos theta. Okay, so now we want to take our 2 by 2 determinant. That's going to look like 2r cos squared theta, and then we've got a double negative here, so plus 2r sine squared theta, and we can factor out the 2r. Say that's 2r times cos squared theta plus sine squared theta, and that's just going to give us 1. So altogether we're getting 2r, and then the catch here is just to remember to take the absolute value of your Jacobian. So you want absolute value of the Jacobian going from your old coordinates over to your new coordinates. And we can say this absolute value is going to be 2r, because when we're working in polar coordinates, r is never going to be negative. So 2r is our correction factor as we move over to r theta variables. All right, and now we're ready to do the fourth and final step where we actually change the variables over. So we can say we had the double integral over this region R of e to the 4x squared plus y squared dx dy. So let's just scroll back for a second and confirm that that's exactly the way the integral was written in the question. Yep, that's exactly what we had there. And we're now going to switch over to our new variables. Okay, so let's think about the three things that are required. So first of all, our integrand is going to change. We decided in step 2 that our new integrand was going to be e to the 4r squared. So let's get that on there. We decided in the first step what the range of values or the limits of integration would be for our new variables. So let's make sure to put our dr and d theta on there, and then we can say the r values are going to go on the inner integral, theta values on the outside integral. So r is going from 0 to 1, theta is going from 0 to 2 pi. Okay, so that part is done. I'll just underline things as we do them. So we've done our limits of integration, we've done our integrand, and the next thing we need is our correction factor. So we decided in our previous step, our correction factor would be 2r. So that just gets multiplied on there. And now we're ready to do our double integration. So let's keep our outside integral on there. We'll keep our d theta on there, and we'll just work on this inside integral. Let's highlight it. So just integrating with respect to r. We went through all the details of the substitution. We would find this would be e to the 4r squared over 4. But let's see if we can figure that out a little more quickly. So if you wanted to integrate this, you would say, well, imagine if I were just taking the derivative of e to the 4r squared with respect to r. You would get 8r times e to the 4r squared. But we're not getting 8r e to the 4r squared. We're getting 2r e to the 4r squared. So if we went through all the details of our substitution, we would find e to the 4r squared over 4. Okay, and then we'll evaluate that. R equal 1 and r equals 0. So I might write the 1/4 out in front. Integral from 0 to 2 pi d theta. And then evaluating this, we're getting e to the 4 minus e to the 0. Well, e to the 0 is 1. So we'll just write it like that. Okay, and then home stretch here, our constants are 1/4 times e to the 4 minus 1. We're integrating from 0 to 2 pi d theta, and when we integrate that, we're just getting 2 pi. So final answer would be pi times e to the 4th minus 1 all over 2. So that was our example of elliptical change of variables, helpful when you're trying to do a double integral over an elliptical region. Thanks for watching.